This is John Black, Super Chemist. Sorry I haven't made that many videos in the last couple of years, but I figured this would be a nice easy one. I'd throw it up. It's going to be the last one for the next 8 months. I'm going over how to make free radicals. Now here's a spectrum of the rainbow with the nanometers of light each one represents. And I already went over, I did a video where you can plug this into an equation and you can see how many joules it is. And then you can figure out, what nanometer of light you need to make your free radical. The most important thing is not just, there's two important things, not just figuring that out, but you also have to figure out what nanometer of light will break the bond you are making. Because let's say for you have chlorine and toluene and you want to make some benzyl chloride. You wouldn't use UV light. It is strong enough to make the chlorine break apart to make your free radicals, but it's also strong enough to break away the chlorine carbon bond that you're making at the benzyl position on the toluene. So you wouldn't use UV light. You use something below that. Blue light, violet light, indigo light. I actually did a video where I proved that blue light will make chlorine radicals from chlorine gas, and that's all you need is this blue light. But LEDs, because I've gone over videos, I did a video once about halogen lights. Halogen lights suck, okay? I thought they were okay for some things. They suck, okay? They suck. But it's because most of the light is just all over the place. When you buy LED lights, they have a narrow range of wavelength of light that they're producing. And that's what you really need, okay? A red and blue and even orange are basically grow lights for people that grow like marijuana plants in their house. You can get them on, you can get any of these on Amazon, eBay, whatever. But you got to make sure of two things. One, it tells you the nanometers. If it doesn't tell you the nanometers, then it's not a light that you want. The other thing is, here's a blue one. I paid $7 for this. I got ripped off. Okay. See how the plastic is coated blue? This isn't a blue LED. This is a white LED that has a blue cap on it, so it looks blue. It only cost $7. I know that's wrong now. You need to spend at least $25 to $45 for each light. And you want to make sure that, I don't know if you can see these fins on this. Just little fins. I'll give you a better pitch later on. And look at the bulbs. They're clear. Crystal clear. This is a red one. It gives off light that's 660 nanometer and also 850 nanometer. One is red and one is infrared. And there's the red light. I thought you can actually see it on the camera, but it's very red. Now each one of these bulbs you want to get at least 24 to 28 watts for each bulb. Now this is an orange LED and you can see the fins again on there. And it's clear bulbs. And the range I get is from 620 to 630 nanometers. That is strong enough. I think it's 623 nanometers. And you need to break bromine-bromine bonds, meaning if you had some liquid or gaseous bromine, you could shine this light on it, and it would make free radicals. Probably can't tell on camera, but it's very orange, very orange. I do have yellow LEDs, but you can notice that there's always a range. If you buy a sodium lamp, you will have a specific, you have 589.3 nanometers, and you will also have, I think, 591 nanometers, and that's it, just those two lines of yellow. So as you can see, this is, it's a super narrow range of light. I don't have that though. Same with the green. I don't have an LED green. It'd be 520 to 530 nanometers. I do have a blue one. It's about 460 nanometers. Here it is. You can see the bulbs are clear. And it still has they're black, but you can see it still has little fins going around on the outside. You probably can't see it on camera good, but it's totally blue. totally blue there. And then you got indigo, or where you're getting up. They'll actually call these UV. This one right here, you can see got again the clear light bulbs. And you can see the color, but it's purple. And mine is 395 to 400 nanometer, but you can also get one like this that are 365 nanometers. Again, on eBay or whatever. And it's just sold so you can, shine it. You go to a hotel, you can shine this on the sheets and see if there's any urine or sperm on it or whatever. But just now, when you get up into stronger lights, meaning UV, either 400 nanometers or shorter, okay, now you're talking about germicidal light bulbs. Germicidal light bulbs. You got two kinds. You got the no ozone and you got the ozone. See how it says ozone free on there? That's this one. It gives about 254 nanometers. And that's what it looks like. It's got like kind of two tubes sticking out. It does not produce ozone. Now this one does produce ozone, and you can see it's 185 nanometers. This is actually strong enough to break a phosphorus-phosphorus bond. Okay. This one has 4 tubes coming out of it. You probably can't see it very well, but it looks like the last bulb I just showed you. These UV lights, you do not want to be putting them in your eyes or, shining on your skin or anything. They're too bad. They're too strong. Okay, don't be getting cancer standing in front of these light bulbs for an hour trying to do something. Okay, let's say you have a cup and you have your white phosphorus and you have your water on top so the phosphorus doesn't touch the air. Right? You heat it up to 50, 60 degrees Celsius. The phosphorus melts. It stays on the bottom of the water. You shine your light on it, right? Your ozone light, and it should break the phosphorus-phosphorus bonds out of that P4 to make red phosphorus, right? Red phosphorus is a solid, so it falls to the ground, in your starness, and eventually all the liquid white phosphorus will turn into solid red phosphorus. Now, I never read this in a book. I've never heard of anyone talking about this before, so this is totally my idea. And the reason why I'm saying that is I don't know if it works. I've never done it, but logically it makes sense that it should work. Okay, and sooner or later I will try that experiment. But like I said, I've never done it. But from what I've read in books on what light can do, I looked up dissociation. Energy needed to break a phosphorus-phosphorus bond. It was, it should be able to do it. So we'll see. Anyway, you all have a great day, and always remember, science is great.